want to welcome you to my lecture today. Of course, today the focus is going to be on hypergeometric distributions. On Monday, we started discrete type probability distributions. I think I'm going to let you know this. Generally speaking, we got two types of probability distribution. We got a discrete type probability distribution and the continuous type probability distribution. So this week we're working on the discrete type probability distribution. Of course, on Monday we work on Bernoulli, binomial, and multinomial. We're going to continue from that today. So the focus today is going to be hypergeometric distribution. Hypergeometric distribution, of course, you can actually say this in chapter 5 of the textbook. Okay, so in the outline, I'm going to walk you through the properties of hypergeometric distribution, then illustrations. But before I get started with this, okay, I have an announcement, but I'm going to make that announcement after the lecture. So what is the essence of probability distribution in the first place? You know, we live in a stochastic world, right? We live in a world where there's a lot of variations. And because of that, we basically need a probability distribution for us to be able to understand how systems work. If we identify a random variable, we need to be able to ask ourselves, is this random variable a discrete or continuous? If it is a discrete, then it means it will random variable must have come from a discrete type probability distribution. Okay, it's just like somebody if I meet a guy and he said he's from the Midwest. Now, what do you think is going to come into my mind? Then I'm going to say, oh, you're from the Midwest. So say that you are from Minnesota, Illinois, so, Wisconsin, Michigan, and the like. So the same thing also applicable to a random variable. If a random variable is a discrete type, of course, it must come from a discrete probability distribution, which could be either binomial, multinomial, hypergeometric, and so on. Now, how do we know if it is from hypergeometric distribution? You know, the same story is more or less like somebody who is from the Midwest in the United States. How do we know that particular guy is from Minnesota? Does that make sense? That is what we want to. So when we're talking about hypergeometric distribution, you know, hypergeometric distribution share the same property with binomial distribution. You know, when you look at binomial distribution, we're actually talking about modeling situation where we have two dichotomous outcome, okay, where we got two possible outcome. Of course, in hypergeometric distribution, we also talk about that. But the only difference between binomial and the hypergeometric distribution is that in binomial, sampling is done with replacements. But in hypergeometric, the sampling is done without replacements. When I choose, I don't replace. Okay, that is what it means. And I want to tell you that is what we do in survey. When you are investigating, okay, or maybe you're conducting a survey, you want to ask respondents question. The moment you ask somebody question, that person will be discarded, okay? Because if you don't discard that person, if the person still remain in your sample, you know what is going to happen? There's possibility your population, then you could choose that person again, and that may amount to waste of resources. Okay, now I want to start with something from an on. Take a look at this. We got a lot of balls in this particular, container, but these balls are of two different colors. Okay, we got green balls, we got blue balls. In general, we have the idea of the totality of the balls. We got 1,000 in this on, 700 green, 300 blue. Of course, if I close my eyes and I decide to pick a ball at random, of course, the probability of choosing maybe green is basically going to be the ratio of the numbers of green to the totality. Okay, and that's why you see 700 divided by 1,000, which is 0.7, right? Okay, but take a look at this on now. Okay, you basically we're basically going to see that if you decide to pick from the top, okay, you are more or less likely to choose blue if you take a look at this now, because if you take a look at the top, you're basically going to see that that is densely populated with blue, right? Okay, that's exactly what I'm talking about. So which we make the probability of choosing blue, okay, to be huge. And that was why I said they all need to be well mixed. If you basically want to introduce randomness, right, then the all need to be well mixed. Does that make sense? So if you don't do that, if you pick from the top, then the chance of the blue is going to be higher, okay, than in the number in the population. Even though the numbers of blue in general is small compared to the numbers of green. How many blue do we got? We got 300 blue, right? We got 700 green, right? But when you are choosing from the top of the horn, the probability of choosing blue will be more than the probability of choosing green. Even though in general, when you want to look at it in general, want to go by the numbers of green and blue, of course, you're basically going to see that the numbers of green is more. Okay. Now, what actually distinguishes between binomial and hypergeometric is that depends on your mode of sampling. Okay, because of that, I basically wanted to see sampling with and sampling without replacement. Now, in blue, I'm trying to demonstrate, the idea behind sampling with replacement. Sampling with replacement is more or less like you choose and you replace. When you replace, you still have the totality. Okay, but when you choose and you don't replace, of course, you are not likely, you are not going to have the totality anymore. And when you are dealing with a sampling with replacement, we expect that the probability will remain constant, right? You remember in binomial distribution that we did the other time, we said that from trial to trial, the probability of a certain characteristics of interest is basically going to be constant. Okay, so what is the takeaway from this page? The takeaway from this page, if you look at sampling with replacement, the probability, if the interest is on green, the probability is basically going to be 0.7. And since I choose and I replace, that probability will remain the same from trial to trial. But when you take a look at the sampling without replacement, initially we got 1,000. If you pick one ball and you don't replace, the population is going to be going down. Okay, so the takeaway is just like when I'm sampling with replacements, I'm actually going to use binomial, because using binomial, we expect that the probability should be constant from trial to trial. But in the case of sampling without replacement, you're basically going to use hypergeometric. Now, how does this work? Then we want to use the formula for binomial now. And we're also going to use the formula of hypergeometric. And we basically want to see whether we're going to get the same results. We are not likely going to have the same results. But we got condition under which the result can be the same, Okay, I'm still going to tell you. Now, in the horn, I got 1,000 balls. 700 of them are green and 300 of them are actually blue. And I take a sample of 7, right? Okay, the 7 is basically going to be, you know, the sample size. Okay, and what is the probability that it has 3 greens balls and 4 blue balls? Okay, of course, if I want to go using binomial, where I'm actually assuming whether the sampling is done with replacements, of course, the formula for binomial is basically going to be n combination x, p raised to power x, and 1 minus p raised to power n minus x. Give me 1 second. I'm going to write that on the board now. Okay, so using binomial n combination x, p raised to power x, 1 minus p raised to power n minus x. Of course, when you take a look at this is the probability, okay, of x equal to that. Don't forget, x start from 0, 1, 2 to n. Okay, now here the probability of green, okay, and picking 3 green and 4 blue, okay. So I'm actually going to say, okay, I let my x to be numbers of green, okay? Then when I plug in the values, don't forget the probability that we're using is p, which is 0.7, okay? Now I'm using the 0.7 here because I'm taking my x here to be numbers of green, okay? If x is the numbers of green, then n minus x would be numbers of what? Blue. Does that make sense? Okay, when I add them up, that become my sample size of 7. Okay, the numbers of green, okay, we said 3 green and 4 that, okay, and because my x is basically the numbers of green, it means the characteristics of interest is green. Then I'm actually going to use the p, the probability of getting green in general. The totality is 1,000. Look at that. There's a difference between an uppercase n and a lowercase n. The lowercase n is a sample size. An uppercase n is the totality. Does that make sense? Okay. And if k here is the total, is the numbers of the characteristics of interest in general, that is the numbers of green. And of course, the numbers of green is 700. You can see that. So my P is basically that initially. So that was why you have a 0.7. So that very P is what I'm using in the binomial formula. Okay, so when you use binomial, you're actually going to get 0.0972405. But if you want to go by hypergeometric, okay, we're actually going to partition, okay, if you want to go by hypergeometric, so we basically going to partition, okay, we're gonna partition this into I got green, okay, and I got blue, okay. Now how many green do we have in general? Okay, we got 700, right? You got 700. And how many blue? We got 300. Okay, so if you add that to that, that's basically going to be 1,000. So we say we want to choose 3 green. If I'm going to choose 3 green, then that will come from the population of green. So I'm going to choose 3 from here. Then I want to choose 4 from here. Okay, divided by the totality that plus that. So 1,000, then that plus that 7. So which means in general, I'm actually choosing 7 out of 1,000. This is hypergeometric now. So, this formula now find the probability of choosing 3 green and 4 blue. Okay, that's exactly what is computed. Now, the result that we have now is basically 0.0969179, even though they are very close, but they are not exactly the same. Any question? Okay, now I want us to focus on hypergeometric now, because practically speaking, okay, hypergeometric actually work because on the field we normally sample without replacements. Okay, now because of that, I want us to focus more on the hypergeometric. If you take a look at the notations, I wanted to play with the notation. In the notation, we're going to have something that has to do with the population sample. We got some notation for population. We got some notation for sample. Okay, so the first one, n balls, that very uppercase n is basically going to denote the totality, okay? And of course, the lowercase n is the sample, okay? And of course, the characteristics of interest, even though there are 2 possible outcomes, there's going to be an outcome that you are interested in. That K will represent the outcome you are interested in. Okay, K green, then N minus K basically going to be the one you are not interested in. And of course, P is basically going to be the ratio of that to that. Now, if we have the same, take a look at the sample, okay? Therefore, when you take a look at the hypergeometric formula now, the probability distribution of a random variable, okay, that follows hypergeometric distribution is basically equal to the probability of S equal to K, as you can see displayed. Okay, and you know what? The expected value of X is going to be NP. There's something I want you to take note. The mean of binomial distribution and the mean of hypergeometric distribution are the same. NP, can you see NP? Okay, but their variance are not the same. The variance of, if you remember what we did on Monday, the variance of binomial was actually NPQ, right? The variance, if I have a random variable X that follows binomial distribution with parameter N and P, expected value of X equal to NP, the variance of X is NPQ, that we can also write as this, okay? This is for the binomial, okay? But in the case of hypergeometric, okay, they're not the same. Look at that. The difference is this guy here divided by this. That is different. Okay, this is a different. Okay, when you look at the hypergeometric variance, you got NP 1 minus P, but in addition to that, you also have those ones. Does that make sense? Okay, so which is basically going to tell you the variance of the two are not the same, but the mean basically the same. Okay, so this is another demonstration of what I just did right now. Okay, using the hypergeometric distribution to figure out the probability of choosing 3 green and 4 blue. Okay, but if you don't want to use hypergeometric and you just want to use a basic knowledge of probability, okay, that is, in the end, you're still going to get the same result. But this is going to be a waste of time. Okay, why not using hypergeometric distribution? Let me tell you this. The reason why some students believe probability is very hard is because those students find it difficult to identify an appropriate probability distribution. For instance, if you want to solve a probability problem, okay, if you know the right probability distribution, that will be very easy because you're just going to use the formula of that distribution. Okay, now that is that. So all what I'm just trying to talk about is that, you know, the idea of binomial and hypergeometric, actually, they are actually addressing the same thing, but except that one sample with replacement and the other sample without replacement. And because of that, even though they're going to have the same mean, but they will get different variances. Okay. Now, so looking at the results, then we actually going to say, you know, they are very, very close. But do you know we can look at the results of both binomial and hypergeometric at different sample sizes to be able to see where can we actually say the two are equal? Do you know we can have a situation whereby hypergeometric and binomial is basically going to give the same result, okay? But let's take a look at this now. Let's take a look at the first one. When this n equal to 100, like a moderately small sample, you're basically going to see that probability is 1%, right? Why do I say 1%? Don't forget the totality is 1,000. We're still talking about the balls example. So 100 divided by 1,000, what does that give? 0.1, right? So 0.1, that's so that is so when you have this guy now, you basically, when you plot binomial with hypergeometric, you can see they are more or less the same. But what will happen when the sample size increases? Okay, when the sample size increases, you can actually notice the difference. Can you see that? Can you notice the difference, right? When the sample size increases, okay? So which means when you have a very large sample size and you're talking about maybe a variable that have two possible outcome, then you should go with hypergeometric when the sample size is large. And why do you need to go with hypergeometric? Number one reason to go for hypergeometric is because you know, if you want to use binomial formula, when sample size is large, okay, that will be very tedious to compute. And number two reason is just like the variance of the hypergeometric is always going to be smaller than that of the binomial. And you know, in statistical analysis, we normally go with a smaller variance. A method with a smaller variance is actually better. Now, I want to move from hypergeometric now to multiple hypergeometric. You remember the other time on Monday when I was talking about binomial, we also have multinomial, right? The binomial is just going to tell you we got two possible outcomes, but for multinomial, more than two possible outcomes. We also have the multinomial version of the hypergeometric. Okay, situation where you got more than two categorical outcomes and you are sampling without replacement. Of course, you're basically going to use hypergeometric. Oh my God, take a look at this. Now, I'm no longer having two colors, but I'm having more than two colors. I got 500 red, 300 blue, and 200 green, okay, in this on right now. Okay, with that, if I'm going to sample without replacement, then I'm going to use a multivariate version of hypergeometric. Okay, so if I draw a sample of 10 balls without replacement, and I want to figure out what is the probability that I'm actually going to choose 2 red, 3 blue, and 5 green. Of course, that is how to go about that. You can see now I got 3 categories now. I'm still doing hypergeometric, but that is going to be called multivariate hypergeometric. Does that make sense? That makes sense, right? Okay. Now, I want us to go into the application now, because we don't just do probability. You know, when we are doing probability without applying probability, then that doesn't make sense. Now we want to apply hypergeometric now in election. Not only in election, we apply we can apply that in a company that is trying to identify defective from the production process. Okay, but let's talk about election now. Okay, election polls. Of course, you know that before elections are conducted, we normally conduct an opinion poll. Why are we conducting an opinion poll? Because as human beings, we are always anxious about the future. Oh, who is going to win? Oh, is my favorite candidate going to win? Stuff like that. Okay, now take a look at this. A poll is taken before an election to estimate the fraction of voting for each option. Should sample be done with or without replacement to avoid polling the same person twice? I told you the other time, if CNN, MSNBC, Fox News, and the like, if they basically want to conduct an opinion poll before the election, I want to believe that basically they are not going to investigate, they are not going to interview every American. They're basically going to select sample, right? And when they select sample, I want to believe the moment they interview this person, that person will be discarded. What are they trying to do? That's a sampling without replacement. So which means the idea of hypergeometric distribution is basically going to work here. Okay, because we don't want a situation whereby we are pulling the same person twice. That is going to amount to waste of resources and time. If the sample size is much smaller than the population size, then we can use binomial distribution. Don't forget the other time, when the sample size is small, the idea of binomial is basically going to work. But when the sample size is large, then we need to go for hypergeometric. But let me tell you this, how small is the small? How large is it large? Okay, when the sample size is 25. Okay, when it is more than 25, we don't recommend binomial. Does that make sense? We recommend hypergeometric. Okay, so complication in using balls in and on to model a pool include, like for instance, if I basically want to use the idea of green ball, blue balls, and I basically want to actually reciprocate that for election, so which means I'm actually trying to classify eligible voter into whether they're going to vote for A or B, then that may be misleading, because we're actually going to have, there will be some individuals that are not voter. Does that make sense? So if you take a look at that, A, B, okay, then there's another individual that are not voter. Okay, so, and that is why complication in using both, because some pollster, they normally use the idea of that, but that could be complicated. Okay, and sample may not be representative. Okay, pooling based on geography, landline, cell phones may give a different proportion in sample than the population. Don't forget, like you're taking sample, okay, it is not everybody that use cell phones and so on like that. We got to make sure that we actually use a sampling technique that can guarantee a representative sample. Does that make sense? Because at times, when you conduct an opinion poll without using a sample that is representative, you're actually going to mislead. And that is the reason why at times they're going to say, oh, this candidate is going to win, and the other candidate now wins in reality, because the sample they select is not representative enough. Okay, I want us to move right now. We're now focusing on hypergeometric distribution, which is the right probability distribution when it comes to election polls. When it comes to figuring out the certain characteristics of interest when your sampling is done without replacement. Now, if we're focusing on, we're still talking about the on example. If I'm focusing on green, then it means it's either green or no green at all. Then I'm actually going to use a labeling one that actually going to call what do we call dummy? One represent if the height ball is green and zero otherwise. Otherwise, it could be something else. Does that make sense? So we're actually going to use the idea of 1 and 0. Okay, you're using the idea of 1 and 0, then you can see Bernoulli in hypergeometric. You can see Bernoulli in hypergeometric, because the other time when we talk about Bernoulli, okay, the idea of 0 or 1 is there because you perform experiment once, right? Okay, when you perform experiment once, when the numbers of trial is 1, okay, it's either you see success or not, which means S can be 0 or S can be 1. Okay, so what was the probability of X equal to 1? That's going to be P. And what is the probability of S equal to 0? That will be 1 minus P, right? Okay, what does it mean? The expected value of S is going to be P. You know, we derived that the other time for Bernoulli, right? Okay, now that expected value of S that is equal to P, okay, that does not use information about the other balls. Focusing on Bernoulli binomial, we're only focusing on certain characteristics of interest. Does that make sense? We're not interested in the other one, okay? And therefore, we're going to say it is not a conditional probability. It is not. Remember the other time, when you are sampling with replacement, then you can talk about independence. When you are sampling without replacement, then you talk about dependence, which is conditional. Does that make sense? Okay, now, if I want to go from Bernoulli mean to binomial, okay, then I'm actually going to add P. Of course, I'm actually going to have NP, right? And what is P? P equal to K over N. I wanted to take note of that. But let me tell you this. Whether we're talking about binomial or talking about hypergeometric, they have the same mean. But let's look at the variance. Do you know why binomial and hypergeometric do not have the same variance? Oh, because in binomial, we talk about independent, right? When you're talking about independent, what happens to covariance? Covariance is going to be 0. But in hypergeometric, where we don't talk about independent, where we talk about dependent, where we talk about conditioning, what happened? Then the covariance will exist. Does that make sense? And that is the reason. Now take a look at, I'm going to walk you through this for general formula now, what we've done before. If I have a random variable X, and what is the variance of the addition of all of that? The variance of addition of all of that is basically going to be equal to the sum of the variance plus 2 summation covariance. But let me tell you this, situation where they are independent, what will happen to the covariance? It should be 0. For binomial, covariance is 0, right? Because they are independent. But for hypergeometric, covariance is now 0. Does that make sense? So which means we need to determine the covariance. Now, generalizing now, if I have 2 variables, U and V, okay, where U and V depends, then I'm actually going to have the variance of U plus the variance of V plus the 2 covariance. But in a situation where they are independent, what is going to happen? Then the covariance is going to be 0. Any question? Did you get that? Okay. Now, we now want to derive, okay, the variance aspect, because the variance of the totality will be the addition of the variance plus the two covariance. If I want to figure out the variance aspect now, okay, the variance of xi is basically going to be that, which is more or less like NPQ. I mean, which is more or less like PQ. So okay, look at that. Oh, give me 1 second. I think I got a notification for. Okay, I hope it's basically gonna last. Let me see. Okay, I think I'm quickly gonna. Okay, now after that, now we want to get the covariance. Of course, we've done it in this class. What is the covariance? Expected value of a product minus the expected value of X, the expected value of that. What is the, now our XISJ, don't forget, product will be equal to 1. If XISJ equal to 1, it will be equal to 0 otherwise. Now I want to find the probability associated with that. Now, the probability is just going to be, when I choose, the first one is going to be K over N, but don't forget I don't replace, right? What will happen to the population total now is going to be N minus 1, and K is also going to go down. Is there anyone who does not understand how I got the probability SISJ to be K into K minus 1 divided by N into N minus 1, because I'm sampling without replacement? Does that make sense? If I want to choose the second one, the population is going to go down. Now, what is the expected value now? Okay, the expected value will lead to that. Okay, and what is going to be the covariance? The covariance is expected value of the product minus the product of the expectation. Of course, the expected value of X, I, is the same thing as expected value of Sj, which is going to be K over N. So K over N multiplied by K over N, that will be K over N squared. Then the expected value of the product. By the time you simplify that, you get the covariance. Look at that. Now, when you get the covariance, now you are now set to combine the covariance with the initial variance that you have. You know, some of you may be wondering, where do I get N into N minus 1 over 2? I'm going to show you now. You know, summation, summation that you actually see. If I want to select 2 from N, okay, if I want to select 2 from N, this is going to be N factorial, N minus 2 factorial, 2 factorial, okay, and this guy can be written as N into N minus 1, N minus, to obey this guy, divided by N minus 2 factorial 2. This cancel that. What do I have now? N into N minus 1 divided by 2. Okay, that is how you got that. You see N into N minus 1 divided by 2, because you want to choose 2 out of N. Does that make sense? Now in the end, by the time you combine that, you have the variance of the hypergeometric. Is there anyone who doesn't understand how we derive the variance of the hypergeometric? You know, the only difference here is just like the covariance exists, because hypergeometric involves sampling without replacement. And when you are sampling without replacement, then we don't talk about independence anymore. And when you don't talk about independent anymore, the covariance exists. And that's why you have that. Okay, so I'm going to walk you through. Now, when you're looking at the properties now, we got the mean, we got the variance for hypergeometric. And another application of hypergeometric is in acceptance sampling. You know, when you find yourself working in an engineering firm, where they are into production, and they basically want to figure out whether they should accept what is coming from the production process, that they're basically going to decide on the highest number of defective they can tolerate. When the numbers of defective is less than what they specify, then they're basically going to accept the loss. Of course, the idea of hypergeometric distribution can actually be used here because they're basically going to be sampling without replacement. Now, take a look at this example directly from the textbook. A particular part is used as an injection device. It's sold in lot of 10. The producer deems a lot acceptable if no more than one defective is in the lot. The sampling plan involves random sampling and testing 3 of the parts out of 10. If none of the 3 is defective, none of the 3 is defective, the lot is accepted. Let me tell you this. When a quality control officer inspects, they don't carry out 100% inspection. They're only going to take a sample. Okay, when they take a sample, they're going to take a decision that, okay, you know what, from the sample that we choose, if the numbers of defective is more than they specify, they will not accept the entire lot. Does that make sense? Okay, so that's what is done here. Now here we want to find the probability that the sampling plan found the lot acceptable. Okay, because before what you produce, before we're actually going to, before they're going to be introduced to the market, of course, we got to make sure what you produce, they are of good standard. And that's why every company into production, we have a quality control officer. The quality control officer, we're actually going to need to be statistically guided. Of course, it's going to use the principle of hypergeometric distribution because it's going to be sampling without replacement. Now, this is the probability now. What is the probability is equal to 0 is